Welcome to PdMA Corporation, home of the MCEMax. I'd like to thank you for joining us as we continue along in our presentation series. Once again, we have the Vice President of Product Development with us, Mr. Noah Bethel.
Hello from sunny Tampa, Florida.
And I am Todd Gunderson, the Vice President of Sales and Marketing, and glad you guys are joining us. We're coming to you right before Super Bowl weekend.
Super Bowl Sunday's on us, isn't it?
Any crazy bets out there, Noah?
Oh, I have a few bet squares that I'm hoping to win with.
Well, I have an 8 and a 1, and I'm sure I'm not going to win with those, but hopefully somebody's going to shine down on me. 28-21, I feel it in my bones.
Could happen.
Anyways, once again, our customers come through for us, Noah. They really do deliver with some great case studies, some great data, and this is no different. Troubleshooting a failed induction motor, it comes from a pulp and paper facility.
Always a good industry with a lot of exciting motors.
Yeah. So this is the problem. Vibration team calls out a problem with the motor. You see 1 foot away, you get an audible noise. Critical motor that is used in many different applications. So
classic start, right? We got vibration testing usually on a monthly basis. A lot of times they hear something they don't like. Let's correlate with electrical. See what happens.
We always are talking about correlating technologies, correlating data. Here's the nameplate. We're talking about a 200 horsepower low voltage motor. That's a pretty big size.
It is, yeah. That's a pretty decent amperage and 6-pole motor, and it's nice to see that they got the bar count.
Always going to call this out, right? It's so important when you develop that relationship with your motor repair facility that you're trying to figure out how many rotor bars are in there. It helps you when you're looking at eccentricity frequency or rotor bar pass frequency. You want to know how many bars are in there. So anytime you can develop that great relationship with your repair facility, we encourage that. So here's our data, Noah.
Wow, that's a lot of peaks, a lot of activity around that line frequency.
Yeah, it's a really elevated pole pass sideband.
Well, we put the red line for a reason there, right? It's above the red line, so it demands attention.
Demands attention. Now, what about the speed?
It is very interesting. Nameplate speed, which comes from the manufacturer, is 1185. And now the operating speed is at full load. This is where we're expecting the motor at the existing performance where it's running at. So it's like it's nearing a 20 RPM lower than expected speed for this motor.
So when that happens, we kind of start to think, well, we got some rotor bar issues, right?
Usually load or rotors, right? I mean, it's something that's affecting the torque, and it could be a reflected impedance or a load issue.
So is it overloaded? Well, it's at 63% load.
Starts to smell more like rotor, doesn't it?
Smells like rotor. Demodulated look. This is another, like we said, we want to correlate with different tests. Well, this shows up.
Running another look of current, it's stripping out the line frequency. It really clears up the what we like to say the severity indication of the potential rotor defect. And 2.5 almost dB. Keep in mind, we start to get concerned around 0.3. So this is what, 8 times higher than what we'd expect.
So we're really gearing up towards a rotor anomaly here. And fifth harmonic. Boy, we're really interested in this level.
Yeah, the classic swirl effect is a good follow-up to a pole pass frequency to try to confirm that it's not just mechanical. So it's always a good thing to look at where these X's fall, make sure that there are peaks associated with them.
And the spacing between these 3 peaks, what's the importance of that? Is there a specific frequency you're looking for?
Absolutely. These are based directly from the slip and the pole pass frequency. So whatever you see as the pole pass frequency from your demod spectrum should be the same distance between each of these 3 peaks.
All right, and I think we have that here.
We do. What'll happen sometimes when defects become worse, our fifth harmonic starts to get a little smeared, and that's natural because the speed starts to vary. And so as a result, sometimes our X's will fall to the side one way or the other of the swirl effect, but the math still works.
Well, we went through a lot of data, but we like to also make this accessible to regardless of your level of knowledge. And we're always going to throw an ocular fault zone view out there for you. Tell us the importance of this, Noah.
What we really like about this is it kind of steps you back, like you said, 30,000 feet, right? Let's look at it from a higher level. Not knowing what a spectrum is, this basically has built-in technical assistance and analytics to give you a software evaluation of the data that was received. And so we break it down into 6 fault zones. And you'll notice, of course, right at the top, rotor is in red. And this is driven by the software analytics automatically. So without knowing a lot, you can simply click the red rotor, and it pops up a pole pass amplitude indication as to what is driving that red indication.
Yeah, and if you want to proceed from here, you can look through all the different testing to kind of just what we did. You can drive it all out of this Ocular fault zone view. So we bring it to the shop. Boy, we pull the rotor out. Nothing really too obvious here.
Make you a little nervous if you were the one making the call, right?
I'd be like,
nervous. A little crack there, but nothing. No, what appears to be not a lot of heat related damage, and I'd be a little nervous if I was the first one to take this open.
Yeah, but we knew based on the data, the vibration, everything is pointing to we've got some significant issues. So the next step was we're going to cut apart some of this and dive further, and boy, thank goodness they did, right?
Yeah, look at the depth of that crack. What's interesting is the crack that's running along there, yeah, exactly, following that mouse, that is hidden under the surface, but a significant separation in the bar itself.
And here's another view of it. They just pulled that right off.
Wow, that doesn't look like a deformed crack. It looks like like it just snapped. Right, and one of the things that we know happens is axially these bars tend to stretch out, and if for some reason this bar is not stretching with the rest of the bars, then it tends to literally crack the bar open, and that's going to create obviously some major current flow problems.
So once you put that replacement in, it's important to get that next baseline, right? Because we want to start out with a baseline. Everything's looking pretty smooth, well below the red.
X marks the spot.
Swirl. There's not really a whole lot going on here with Swirl.
Right. There appears to be some peaks, but they're well below the blue observed line. Not that that's a direct correlation, but again, we need a lot more definition before we'd ever get concerned about it.
Nothing truly defined.
Right.
And demodulation, remember we were at 2.5. Now we're really down in the very low levels. Almost
unseen. I mean, this motor is running smooth, so the audible noise that the analyst or the technician was hearing is going to be gone. So everything's looking thumbs up, looking good.
And then, interesting here, a rotor influence check. Now, we are always encouraging our customers to do at least a baseline. We understand that it's a time-consuming test, but if you can get a baseline on that, that helps you out.
Right, and being an offline test, sometimes you're in these situations where you're not going to get a running test. And you look to the right graph there, and one of the things we got on both of these is a low influence warning. And the low influence warning says, hey, there's not going to be a lot of varying sinusoidal activity, but it's important to have a baseline to compare it to. Because you look at the one to the right, almost no sinusoidal activity whatsoever. But the one on the left, you start to see a developing sine wave. And from a low influence with a little bit of sine wave activity, tech support's going to say, hey, let's put it in observe until we can look at your pole pass, look at the swirl, look at the demod, which they did.
Yep. Now, we are always saying what? Justify, justify, justify.
Absolutely.
Why are you in business? It's to save the company money. If you're in a reliability program, your main goal is to keep the plant running efficiently, smoothly, and with the least amount of cost. So when you can have a cost avoidance, in this case, of $30,000 per hour saved at a total of 4 hours that it would take to replace this, you're talking a total cost avoidance of $120,000 US.
And that's a big deal. That is a big deal, and they were hearing this, so it was getting closer and closer to the end of life had they not got the information they needed.
Yeah. Well, this was a great presentation. Once again, we hope if you are making some crazy bets at the Super Bowl that you're a lucky winner. I know Noah hopes he's going to win.
I'm sure I'm going to win.
I know. I hope you don't, because I'm in the same pool you're in, and I win, maybe. Anyways, we always thank you for your time, and if you guys have any other data that you'd like to share with us, or case studies that you feel are interesting and would be welcome to the rest of the group, or a tip of the week that you think is of value, we would certainly love to hear from you, and you can contact us at the numbers that you see on screen. As always, we look forward to the next time that we see you, and until then, please stay safe.